Okay, so I'd like to come back to this slide where we looked at the two masks, and then to jump into just correct one error from the last board scene, which is here. So I had issues with the pen. So please note that the sketch showing that operation of taking an image and convolving it with two masks, taking the two outputs, so you have the row and column coordinates of gradient field at every point in space. That is, this should have had a subscript n here to match, to go with the HM, which then matches with the two masks I've just shown you back here. So make sure that you correct that omission. Okay, so what we've looked at is how to map an image to a gradient field by using a pair of convolution masks. And that now sets the stage for us to consider the topic of edge detection a little more formally. We're not going to go into a huge detail on edge detection. You're going to have a practical in which you explore how edge detection is performed, starting with actually one-dimensional signals and working up from there, and also making clear that you understand the difference between convolution, which is a strictly linear operation, and how you can view convolution and relate it to taking a derivative, or actually in the case of the practical, a finite difference operator. And then you're going to move on to calculating a gradient magnitude field and estimating the direction of the direction of the gradient vector in that from an input image. So the two masks I've shown you before are sometimes referred to as edge detection masks, but they aren't edge detection masks. So let's be clear. What they do is they allow you to get an estimate of the gradient field of an intensity image. Edge detection itself can be thought of as a simple type of segmentation operation. You have to make a decision, and the decision allows you to split the pixels of the image generally into two classes, edge and non-edge. And so in the simplest case, the way that you perform edge detection is or what you expect as the output of an edge detection is somewhat similar to our second chapter, where we looked at performing a decision as to or separating images into two classes, object and background. In this case, you're separating into two classes, edge and non-edge. And that's the simplest form of edge detection that one can come across. Most edge detection processes start with the application of one or more linear convolution operators, and therefore a convolution mask, one or more. And edge detection is then performed on the outputs of those convolution operations. So what is an edge is the first question. And an edge is really a straight or curved boundary between two regions of an image that have different average properties. Now those average properties could be color. In the case of a grayscale image, the property in question is often the average pixel intensity, but it can be some other derived quantity, such as a textural property that changes between one region of the image and another. We will assume that the edges that we're going to consider in this section are characterized by changes in average image intensity. Given that, we can look at 5 broad classes of edge detector, but really there are only 2 that are in wider use. So the more common ones are gradient-based and zero-crossing-based. We're going to look at those in a bit more detail. There are some lesser-known techniques which are based on differential invariance, so treating the intensity image as a surface and then using differential calculus of surfaces, I guess it's just geometry, but differential geometry, in order to define measures that you can compute on those surfaces that allow you to distinguish between distinguish where an edge might occur in the image as a surface. There are also phase-based techniques, which generally rely on a technique similar to the notion of phase and the use of phase in Fourier transforms, but which is actually about using local phase properties. And then there are surface fit techniques. So you can fit a surface to your intensity as a function of x and y, a bit like the bilinear model that we looked at in chapter 1. And then you can use, once you've done that fit in a local neighborhood, you can look at the coefficients of the fit. So if it's a bilinear model, you would look at your A1 and A2 parameters. If it's a quadratic model or some other model, you look at parameters associated with rapid rate of change of intensity as a function of spatial position. And so depending on the surface fit technique you use, you basically use the coefficients of that fit to say whether there's an edge or not. But let's look at these two more common techniques up here, gradient-based and phase-based. So in gradient-based edge detection, you effectively will make use of a pair of convolution masks as a minimum. Now you can use more, so you can use 4 masks, you can use 6 masks, and so you can actually use a variety of different convolution masks, and then combine the outputs from those masks to make an estimate of the gradient magnitude field. To decide whether or not you consider that in a group of pixels or within a certain neighborhood region you have the presence of an edge, then you apply a threshold process to the gradient magnitude field. And that will allow you to say which pixels can be considered to be close or on an edge. And then normally there's a final step in that process, which is called edge linking. And in edge linking, what you tend to do is you take all the regions or the pixels that satisfy the threshold property of having a large enough gradient field, and then you connect pixels together into single coherent edges based on whether they share similar or smoothly changing gradient field directions. Okay, now we won't look at edge linking because it's a quite advanced topic and there are lots of other things you can do without having to rely on explicit edge linking. So we're just going to look at the first principle, which is the gradient mask idea. So let's jump to this to show in grayscale we have let's say this is some direction that we can move in the image as a function of spatial position. So this could be in any direction. So the n simply refers to position along a chosen direction in the image space. And we define an edge as being somewhere, some place that we have an intensity change. Now the intensity change is likely to be not instantaneous. It's going to be over some spatial scale. And the question is, where do you define the edge as being? So you can define the edge as being anywhere that the gradient magnitude, which is shown in the first red dashed line, where that exceeds some threshold level. And that will give you a region in which, or a group of pixels, so there's a certain thickness to the edge. And you can say, okay, within this chunk of pixels, I have an edge occurring. But you could do something a bit more sophisticated. You could also look for a local maximum in the gradient field. So first derivative of intensity is this red trace here. I said this is gradient magnitude. In fact, in this case, because the gradient or the intensity is only increasing or 0, then our gradient magnitude is equal to the first derivative of intensity. We've got nothing that's negative. So it's either 0 or it's positive, and so gradient magnitude and first derivative of intensity are the same. And so you can see that if we set the threshold to be, let's say, at this level on the first derivative axis, then everything between here and here, so let's just draw a dotted line here just to make this a bit more concrete. So let's say I I set a level here, and I say anything above this level I consider to be an edge, then it means that our edge is going to have a certain thickness that's between here and here along this this direction or spatial position axis. Okay, so we will get a thick edge. Whereas if we set the threshold up here, then we would end up with a thinner edge. So that's kind of arbitrary. And a better solution is to actually find a local maximum in the first derivative of intensity that will correspond to where the rate of change hits a maximum. So that's one refinement. But generally, we don't want to do that just on its own, because when you apply a gradient operator, as you'll see in the practical, the result can be quite noisy. And so often you want to look for local maxima of the gradient, the first derivative of intensity, but do that only within a region where the gradient itself, the gradient or the gradient magnitude exceeds a threshold. Okay, so that's one approach. The other approach that we can use is if you look at this graph here, so the gray is the intensity, the red dashed is the first derivative of intensity, and then the second derivative of intensity is this orange trace here. So for that second derivative of intensity, what we would do to localize an edge is to look for what we call a zero crossing. So a change in sign of the second derivative. And where that change of sign occurs, we define that location as being an edge location. And of course, you can actually combine that with also having a threshold on the first derivative of the gradient magnitude as well. So let's come back to summarizing that. So with gradient-based edge detection, we have the issue that, although it's the most commonly used technique, it's often sufficient for many edge detection tasks. It does suffer from these problems, so results can be quite noisy. If we only use thresholding, then the edges can be thick, and there are general issues with setting of a threshold too low, and you get either false edges or you get very thick edges, and too high, and gaps may arise in your edge maps. But also, any threshold you set, and if you only rely on setting a threshold, then the edge thickness will also vary even across coherent edges in the image. So one solution to the thick edges problem is to look for local maxima of gradient instead, but you would also combine that with setting a threshold. So you use several operations, if you like, applied to gradient magnitude in order to detect the location of the edge in an image. Okay, so now to do the second order, to get this orange trace, what we can do is use a second order derivative. And you can do this in multiple ways. You can either have a directional second order derivative, in which case you will need several convolution masks that are sufficiently large to be able to estimate second order derivatives. And we'll see that there's generally speaking, when you get to second order derivatives, you tend to get quite noisy results. Unless you apply a bit of smoothing. So we'll look at that in a second. But one of the tricks that's used here is not to take directional second order derivatives, but to use what's called an isotropic Laplacian operator, which takes a derivative as a function of spatial, or a second order derivative, as a function of spatial position away from the center of the mask. And the mask pattern associated with doing that looks something like this. So this is the basic structure of the mask. So if you look at this, you see that you've got negative values in the center and also in the nearer pixels. But then for pixels that are further away, that is the the diagonally connected pixels within a 3x3 neighborhood, you see that you have a change in sign, so you use positive values. And again, the magnitude of all 4 of these corner pixels is weighted the same because they're at the same distance away from the center. The B's are also weighted the same, the B pixels, because they're at the same distance away from the center of the mask. And the center of the mask itself is weighted with a negative value, which tends to be the largest magnitude value in the whole mask. So your mask pattern might look like this. And here, the sum of all values is 0. So again, like we saw for the case of each of the direction selective Prewitt masks, if your mask is in any region of the image where you've got constant intensity, then the mask output 0. So you've got no rate of change of rate of change, then you end up with the mask outputting a value of 0. So this is what the result of applying a Laplacian mask is to the good old leaf-on grass image. But what you can see it's done is that it's tended to find or to generate large responses in regions of the image where you've got the fine texture of the grass. And actually the result is pretty noisy. So in fact, what this mask is doing is it's also working as a high-pass filter. And it's amplifying regions of the image which have very fine structure, but also it's amplifying a lot of noise in the image itself. Now, in the case of this image, we don't have much sort of sensor noise, but in other cases, for example, in medical imaging, this would give you a horrible result. So there is a way to improve this result very simply, which is to go back to our good old Gaussian mask and to combine or to apply that Gaussian mask at some scale sigma. So the mask may be narrow for the case of small values of sigma, or very spatially wide for the case of large values of sigma. And by applying this mask first to the image before we apply the Laplacian mask back here, so apply first a Gaussian mask to smooth the image, and then to apply the Laplacian, you get a much nicer result. In fact, you can combine the Gaussian smoothing with the Laplacian operator here, so you can actually compute the Laplacian of this Gaussian mask, and then get a Laplacian operator, which is known as a specific type of Laplacian operator, which is known as Laplacian of Gaussian, or LOG operator. And so the LOG operator looks like this with a parameter of sigma. And this is now written using a polar coordinate system where rho indicates distance away from the center of the mask, and the width of the function is controlled by the parameter sigma. So this is what a Laplacian of Gaussian operator looks like. By the way, I've inverted the Laplacian of operator, so Laplacian of Gaussian operator. So these are inverted Laplacian of Gaussian functions, and the way that they're generated is just by taking this expression here, plugging in values for m and n using a center weighted coordinate system. So 0, 0 is in the center of this region here, and then just sampling the values of m and n and then plugging them into this equation with this definition relating this definition of rho. And that's given me this using a small value of sigma, and this using a bigger value of sigma. Okay, so these are the Laplacian of Gaussian masks, and if we then want to apply those to perform zero crossing based edge detection, we first convolve the image with an LOG mask that's of appropriate size. We then find zero crossings in the result of that step, and we perform edge linking. And this is what the result looks like when you take a small value of sigma, and this is what the result looks like when you take a large value of sigma. Now we won't go into how you go about doing the zero crossing detection, because there are some subtleties there about that. So a zero crossing detection means that it's worth mentioning, because if you've never come across this issue, it can surprise you the first time you meet it. But if you're familiar with working with discrete signals and so on, then it won't be a surprise. But if you're not, it is a surprise. So if you've only ever come across the concept of, let's say, detecting a change in sign in something like this, let's take a step back. You might be familiar with the definition from calculus of finding a turning point, which is that you look for the place where a second order derivative is equal to 0. Okay? In a discrete image, you are never going to have that situation. So, the times in which you encounter that situation are very, 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 very rare. What you're likely to find instead is that between one pixel and another, the output of a convolution is going to change in sign, and either side of in both those pixels you have a change in sign. They're next to each other, and either side of those pixels you're going to have fairly large values. Okay, that's kind of what you see in this orange dash trace. But here, if this were a continuous function, then we could find a place where this is identically equal to 0. In a discrete image where you only sample values at particular points in space, you are never going to have a situation that that zero crossing it's going to give you a value that's exactly 0 where the crossing happens, unless you have very, very finite, very, very limited precision in your calculation. You're not going to get that. You're going to get things that fall either side of 0, so positive and negative values, and generally speaking with large values of opposite sign near to them. So the subtlety of detecting zero crossings is not, it takes a bit of algorithmic housekeeping in order to get that right. So we're not going to do that or go into that in the practical. You should just be aware of it. Okay, so I'm going to just wrap up this edge detection thing by talking about two more things. So the canny edge detector is the first thing. So the canny edge detector is considered to be a standard for edge detection. It's based on using Gaussian smoothing and derivatives of Gaussians. And it also looks for local maxima in the gradient magnitude functions. So in other words, coming back to this idea here, okay, with the red dashed trace, the simple thing we do is we set a threshold on the gradient magnitude. The more complex thing is that we look for this location here, some kind of peak that runs through the image. Now, when that peak runs along several pixels within the spatial field of the image, you refer to that as a ridge. So the canny edge detector uses ridge detection, and it also uses a bit of thresholding so that you look for ridges within regions where the gradient magnitude is high. Once the algorithm has detected a ridge, it then tracks along the tops of these ridges and sets to 0 all pixels that are not on the ridge, on the top of the ridge, so you get a thin line in the output. And this process is known as non-maxima suppression. But it can be known as other techniques, so ridge following, things like that would also explain this process. So the canny edge detector, which you can find implemented in many different libraries for edge detection, effectively uses the first order derivatives, but it also uses Gaussian smoothing, and you can set the parameters of the canny edge detector as you wish. Okay, so the Hessian matrix is kind of related to differential invariance, and so with Hessian-based edge detection, you basically use second-order derivatives, and then you use the eigenstructure of that Hessian matrix to determine where an image might occur in the image. Sorry, when edge might occur in the image, or where edges might be found in the image. The Hessian approach is computationally a bit more expensive, but it also relies on using convolution to estimate those first and second order derivatives, and then builds a Hessian matrix at every point in space, and then solves or determines the eigenstructure of the Hessian at every point in space. So a little bit hairier computationally, but is a nice technique to explore if you want to play around with that.